Okay, so we're going to talk about polarity and polar versus nonpolar bonds. The first thing we have to know is electronegativity. Electronegativity when we did the periodic trends section. So just a reminder, it's the attraction of an atom to a shared electron. Okay. Again, fluorine, highest. All right, and noble gases don't have any electronegativity. Okay, the fluorine has the highest, and the noble gases not having any. That is not super important for this section. So to find polarity, got the word find. Now my eraser doesn't work. So to find polarity, you are going to subtract electronegativity values of each element. Okay. So then you're going to compare that value. So you're going to compare the result of that to a chart. And I'm going to write the chart here in a second. So compare the result on the chart. Okay. So this chart that I'm talking about is a very, very simple chart. It's more of a number line. So you can't have anything that is less than 0. So we're going to start at 0.0. Okay, and it goes all the way to essentially about 4. But we're just going to put the arrow out there because we don't need anything past a certain number. So anything from 0.0 to 0.4 is going to be nonpolar. Okay, and I always say that the 0.4, we always go to the left. So if it's 0.4 exactly, it's nonpolar. Okay, from 0.4, technically 0.41, I guess, to 1.7, these are going to be polar bonds. Okay, and again, if it's exactly 1.7, I always just say move it to the left, it's polar. And then anything higher than 1.7 is going to be an ionic bond. Okay, so we've already talked about ionic bonds. So this is your scale, your number line that you're looking at. Okay, so if we did an example, just an example chart. You've got element 1 and its electronegativity value. Then you have element 2, its electronegativity value. The result. Okay. So let's just do a couple of examples. Let's say we have a carbon-oxygen bond. So the first one is going to be carbon, right? And then in your student assignment folder that I've shared with you, you have a periodic table that has all the electronegativities values on it. So you're going to have to look at that to determine what the electronegativities are. So for instance, the one that I'm looking at right now says that carbon is 2.5. Okay, and then oxygen is 3.5. So it doesn't matter which one is first. You just take the big number minus the little number. Okay, so 3.5 minus 2.5 equals 1.0, and 1.0 falls right in this section here. So that is going to be a polar bond. Okay. Let's do another one. Let's say that it is lithium and fluorine. Okay, a lithium and a fluorine bond. Lithium is your first one, and its electronegativity is a 1.0. Fluorine is your next element, and its electronegativity is a 4.0. So 4.0 minus 1.0 equals 3.0, and that is way past 1.7. So this one is ionic. You should have already known that because lithium is a metal and fluorine is a non-metal, which automatically makes it ionic. But if you didn't, you can use it. You can figure it out this way. Let's do a nitrogen and a nitrogen bond. So element 1 is nitrogen, and its electronegativity is 3.0. The second element is nitrogen as well, and its electronegativity is 3.0. So do some simple math. 3.0 minus 4 equals 0. So it's nonpolar. Okay? Nonpolar. You are always going to get a nonpolar bond when the same element is attached to itself. Okay? And then let's do one more. Let's say that we have a formula of Al2O3. Okay? You don't have to do anything with the fact that there are 2 aluminums and 3 oxygens. Okay? You don't have to worry about that. All you have to worry about is what are the 2 different elements. So element number 1 is aluminum, and again, it doesn't really matter which one is first because you're just going to take this bigger number, subtract the littler number, and move forward. So aluminum is a 1.5, and then oxygen is a 3.5. So 3.5 minus 1.5 equals 2.0. So that is ionic. Okay, that's all you have to do. Again, these don't matter. The subscripts do not matter. All you're looking for is the individual bond. Okay, and the theory behind that, not really a theory, the reasoning behind that is because if one of these bonds is polar, they're all going to be polar, so the whole thing is going to be polar. If one of these bonds is ionic, all of them are going to be ionic, and the whole thing is ionic. Okay, so you don't have to calculate every single bond that's in there, just calculate one of them. Okay? Okay, so that is determining polarity using the electronegativity values.